Okay, so in this section we are going to redefine how we talked about maxima and minima. Now if you remember from our pre-calc 1 class that we defined maxima and minima as coming into and going out of with either increasing or decreasing, and we talked about it being an open interval. So we didn't include, when we say open, it just means we don't include the endpoints. A closed interval means that we do include the endpoints. And the way we define it now is that our maxima and our minima are going to happen in which the output is the highest in some closed interval. So if you also remember, the way that we defined our vertical asymptotes and our horizontal asymptotes in pre-calc 1 is different than the way we define it again in calculus. So expect that to happen is that it's not that the definition necessarily changes, it's just getting a little bit more involved. And so we've got a little higher math understanding, so our definitions are going to be a little bit more involved than it was in previous courses. So as you go higher in math, my math major, expect that to happen. It's not necessarily different, it's just more involved. So when we talk about absolute maxima and absolute minima, that means that we are looking for the highest or the lowest point. We are not guaranteed either one of them, but if we are on a closed interval, we will have one of them. So we may have two of them if we're on a closed interval. When we are looking at these particular graphs, we talked about this yesterday. This one has an absolute minima, but it has no absolute maxima. And in fact, this particular graph has no maxima at all because of the fact that there is no highest point. It's going on forever in both the negative and positive infinity. This particular graph does have an absolute minima, and it does have an absolute maxima. Notice when we're talking about minima or maxima, we do not give them as ordered pairs. So if you do write them as ordered pairs on the test, I'm going to mark you off like 1,000 points. Because at this point, it's like 1,000 points, yes. So that means you're going to go negative. You have to go back to pre-calc 1. At this point, you don't write our maxima and minima as ordered pairs. You tell me where it happens. In this case, we have it happens at x equals 0. And you tell me what it is. The absolute minima is 0. And it is at x equals 0. The absolute maximum is 4, and it happens at x equals 2. So you tell me where it happens, and you tell me what it is. You do not write it as ordered pairs. So we have a closed interval. We have closed it. We included the endpoints. When we're talking about closed, we're just talking about the endpoints. So that's this here, is I've included the 0 and I've included the 2. So if I have a closed interval, I have a maxima and minima in this particular case. This one, I do not have a closed interval because both sides are not closed. You will notice here that that is open, it's non-inclusive. So the closed side, I ended up having an absolute maxima, but I do not have an absolute minima because it is not included. And then on this one, because it is on an open interval, I neither include the endpoints. So I have neither an absolute nor absolute maxima nor absolute minima. So pay attention to the intervals, because if you get it marked wrong on the homework and it's telling you on some interval, it may be just because it's an open interval. It's not that you're necessarily doing anything incorrect except for not reading the interval part of it. For this case, I do have a closed on one side. I'm closed on the left-hand side, and I'm not closed on the right-hand side. So I have two absolutes. They're both at the smallest, so we have two absolutes. I'm not guaranteed one. I can have two. And in this case, I have two of them. It is the absolute minimum of 0 at x equals 0 and at x equals 1. Again, because this is an open and non-inclusive, I don't have an absolute maxima. Okay? Last example here. I don't have an absolute maxima. I do have a closed interval on this particular example. I am closed between A and B. I have closed dots on both A and B, both ends, so I have a closed interval. I do have an absolute minima, that's this side. And the reason I don't have an absolute maxima is because this is my highest point, but it's non-inclusive. So that does not have an absolute maxima. This point right below it is not the absolute, because you can see that this part of the graph is actually above that dot. So it has no absolute maxima. Okay. So then we have something called the extreme value theorem. So I'm going to give you a moment to read through the extreme value theorem. So what the extreme value theorem states is that if I have a closed, that means the endpoints are included. It's continuous, that means I don't pick my pencil up from left to right as I draw it. And it's bounded, that means I have a point in which I'm not going to go below and a point in which I'm not going to go above in terms of my y values. Then I am guaranteed an absolute maxima and I'm guaranteed an absolute minima. So if we take a look at our previous two examples, if I look at both of those, they're both bounded, they're both closed, but they're not continuous. These two examples, these last two examples that we looked at, they're both bounded, they're both closed, but neither one of them are continuous. Yes? That means that I'm not going to go up forever or go down forever. So I have a place in which my y values stop in the bottom, or start in the bottom and stop at the top. So if it is closed, if it is continuous, and it is bounded, I am guaranteed a maxima and a minima. Can you still have absolute maxima and minimas when it's not continuous? Oh, absolutely. So I take a look at B here. So my first one satisfies everything that I need. So this graph satisfies everything. It's bounded. It is closed because I see the dots are included on both endpoints. And it's continuous, it's bounded, and it's closed. On B, it is not continuous. It is not closed. It is bounded, and I still have an absolute. So I can still get absolutes even though my conditions are not met. I can have absolutes. But if I am all those conditions, and the three conditions that I have to have is that it has to be continuous, it has to be closed, and it has to be bounded. If those three conditions are met, then I am guaranteed to have an absolute max and an absolute min. Now, in the past, we did not include the endpoints, and because in the past, when we were in pre-calc 1, we didn't include, we said for some open interval. So we never included the endpoints in pre-calc 1 because we said for some open interval. Now we're in a closed interval, so we now include the endpoints. So go ahead and read through this definition. So what this tells us is that we have an open interval now, and the reason we're doing an open interval is because it's a subset of a closed interval. So this is where I'm going to have my locals. So when I'm talking about a local maxima and a local minima, the reason I have an open interval on this is because I don't include the endpoints. So my locals are never going to be my endpoints. My absolutes could be the endpoints, but my locals will not be the endpoints, because when we're talking about local maxima and minima, it is in an open interval, which is a subset of a closed interval. So if I have a closed interval from A to B, the subset would be the open interval from A to B. So I don't include the endpoints. But the way in which we describe the maxima and minima in the local form is that it is still the highest point or the lowest point in terms of outputs. It's always the outputs. It's the x that produces that output. So as an example, here's this lovely, lovely graph. So in this lovely graph, I have an absolute minima. We're on a closed interval from A to B. I have an absolute minima, and that happens at x equals A, and it is whatever that output is. I have a local at C, I have a local at D, and I have an absolute at C, and then I don't have anything happening at B, because it is not the lowest nor is it the highest at B. So my local maxima and minimas, and this is important, can only happen on an interior point. It does not include the endpoints. If the absolutes happen at the endpoints, we call them endpoint extrema. So endpoint extrema. So if you see anywhere endpoint extrema, that means that our absolutes happened at the ends. Endpoint extrema. So again, I have an absolute minima at A. I have an absolute minimum at C, or maxima at C. I have a local maxima at or that's E, I guess. Sorry, that's E. This one is E. So I have an absolute maxima at E, a local maxima at C, a local minima at D, and then nothing happening at B, because my locals can only happen on the interior points. Okay? How are we doing? All right. Our critical points are the places in which the derivative equals 0. And our critical points can only happen on interior points. So when we talk about critical points, when we're doing the derivative and setting it equal to 0, we're only doing it on the interior points. We're not looking at the endpoints. So critical points are the places in which my derivative changes from positive to negative, and in fact the derivative is 0. Critical points are the maxima and minima, and it is the local maxima, the local minima if it's on the inside. It could be absolute maxima and minima if it's on the inside. The interior points, that means I don't get to include the endpoints in terms of my critical points. Here's a nice question I always like to put on the test, true or false. A critical point implies a local maxima or a minima. Yes or no? Well, what does that say on the note? Okay. So moving on. Right here, a local maxima, or excuse me, a local minimum at C, but f of C does not exist. So I don't really have a critical point. So it has to have, the derivative has to exist. And on the first example. The second example, we have a local maxima at C, but f prime of C still does not exist because it is a corner there. So just because I can find a local or absolute does not mean it's a critical point. So critical point means the derivative has to exist there. So if I say a maxima implies it's a critical point, the answer is false. Because we can have a maxima or a minima. It could be local, it could be absolute. But if the derivative doesn't exist there, it's not going to happen. Okay, it's not a critical point because the derivative has to exist. Here, we have a derivative, but I don't have a local maxima or a minima. I have a derivative that equals 0 on this example right here. On this example right here, I have a derivative that exists, but it's just a horizontal slide. So it is not an absolute local maxima or minima. In this case, a vertical slide, we don't have a derivative there, and we don't have a local maxima or a minima. Why is it a horizontal slide can have a derivative, but a vertical can't? Yes? Yep. Horizontal line has a slope of 0. What is the slope of a vertical line? It is undefined. And that's how come we don't have a derivative when we have a vertical slide. It's because the slope is undefined. That gets us to Fermat's theorem, so I'll let you read through that. So looking at this particular theorem, f has a local extrema at C, and f is differentiable at C, then this must happen. F prime of C must equal 0. So if we have a local extrema and it's differentiable, then at that point, our derivative is equal to 0. So those two things have to happen. First, it has to have a local extrema, and second of all, it has to be differentiable at that point. Then we set the derivative equal to 0, which we've been doing for a while. So this is not really anything new, it's just the definitions that we're throwing in there now. We're formally defining everything. We haven't changed much. So can you find a finite absolute maxima? Why or why not? And can you find a finite absolute maxima for the other one? Why or why not? So I want you to talk to your partners on these two. Are you going to find an absolute maxima for a quadratic? Are you going to find an absolute maxima on a cubic. Why or why not? So what do you think? Will I have a maxima? Can I have a finite, meaning that it's a number that I can find numerically? Can I find an absolute maxima for a quadratic? Yes. When does that happen?
When it's negative.
When the leading coefficient is negative. I'm guaranteed, because it's a quadratic, I have one turning point, and so I am guaranteed an absolute maxima, and it's a finite number. It's a number I can actually find. What about cubic? Am I guaranteed an absolute maxima for a cubic? Will I ever have an absolute maxima for a cubic? Yes or no? The answer is no. Daniel said no, and I agree with Daniel. He shook his head. Or maybe he just said, I don't know what's going on. I'm not certain. But he shook his head no. The answer is no because of the end behavior. So cubics are going down forever on one side and going up forever on the other. Depends on what your leading coefficient is. So unlike a quadratic in which we have something that could look like that, we have one turning point. My cubic, just the end behavior of my cubic, if my leading coefficient is positive, it's going to look something like that. If my leading coefficient is negative, all that does is just change the direction, but I'm never going to have an absolute. So the only time I'm going to have an absolute maxima or minima, and I'm guaranteed it, is when my powers are even. So when my powers are even on my polynomials, if my powers are even on a polynomial, I am guaranteed either an absolute maxima or an absolute minima, depends on what the leading coefficient's telling me. So only ones that have them are even powered. So anytime you have a polynomial of degree that is odd, you will never have one. You'll have locals possibly, but you won't have an absolute. All right, I know how you all love to draw these. For the following problem, draw graph f of x, which is continuous, over the interval from -4 to 4, that has these following properties. You have an absolute maxima at x equals 2, an absolute minima at positive and negative 3. You have an absolute, so that's 1. So the A is just 1 by itself. That is one graph. B is a different graph, still going from -4 to 4, but you have an absolute minima at 1 and you have an absolute maxima at 2. C is another graph, still going from -4 to 4. So on C, you're starting at an absolute maxima at x equals 4, absolute minima at -1, a local at -2, and a local and a critical point that is not a maxima or a minima at x equals 2. Think about that one. And then D, absolute maxima at x equals 2, and x equals -3, local minima at x equals 1, and absolute value at x equals 4. So go ahead and draw these, please, with your partners, because you may be asked to put them up on the board. Let's go ahead and take a look. Again, we talked about A on the board, so I'm just going to rewrite it over here for those students that are not in today. I know that I need to start at -4. I know I need to end at 4. I also know those endpoints have to be inclusive. I have to have a minimum at -3 and at 3, and I have to have a maximum at 2. So how far up or down you go is up to you. So I know that at 2, that has to be my high point. At -3 and +3, it has to be my low point, and it has to be the same value. So if I said that's 1, then it's 1 as the lowest point for y on each direction. So I could have a graph that starts like this, as long as it's not as high as, and of course I put it right as high as long as it's not as high as my maximum value. And ideally we're doing smooth curves because that way we can differentiate. And so my graph for A could look something like that. The important thing is that it's continuous. I included the endpoints. My minimas are at the right place and my maxima is at the right place. How was the first one? Okay. Second one, I'm still going from -4 to 4. So on B, I'm still going from -4 to 4. And I have an absolute minima at 1, and I have a maxima at 2. I still have to go from -4 to 4. So I could have a graph that looks like this. I'm going to start there, and my minima is at -1, so I'm going to go all the way to here. I need to max out at 2. So my graph could look something like this. Smooth curve ideally. And that's what my graph could look like. yours could look something different as long as your endpoints are closed. We max out at where x equals 1, and I have, or excuse me, at x equals 2, and I have a minimum at x equals 1, and that those endpoints are in somewhere in that maxima and minima range. Okay? How are these? So if these were on the test, you were like, I got this.
If they stay with
Maybe. Okay. So on C, this is a little bit more involved. So let me do C over here. I still have to go from -4 to 4. So -4 to 4. The thing that changed on C is I have an absolute maxima at 4, so I know I have to have an absolute maxima at 4. I have an absolute minima at -1, so I'm just going to put that on there. I have a critical point that is not a maxima or a minima at 2. So what is happening at 2 if it's not a it's a critical point but it's not an absolute?
slide.
I have a slide.
Good job, Sam.
Good job, you all. So I come down, and then I'm going to slide, and then I need to come down, touch that, and maybe I'll finish right there. So what I have is I have to have a slide at 2. Not a very good slide, but if you look at that kind of tilted and you're sick, it looks like a slide. So in your mind, it's a slide. Okay. Last one, an absolute maxima at 2 and at -3, a local minima at 1, and an absolute at 4. So using this information, so -4 to 4, I have an absolute maxima at 2 and at -3. So I'm going to go up to here. I have a local minima at 1. So maybe right there. And an absolute minima at 4. So maybe here. So this is what mine might look like. So I'm going to start down here, come up, curve, touch, and then come back down right there. So maybe that's what mine looks like. Okay? How is that? How are these? How are these? Not too bad? Okay, so the last part of this, we have a bunch more in this, but we need to, so we'll just power through this. We can do this. So on these, which one of these 3 would you like me to do? Which one of these 3 are you all wanting to do? You want me to do C? I'm going to find the critical points on the domain of the function or the interval that is given. So I need to find the critical points. That means I am chasing derivatives, and I set my derivatives equal to 0. So my tangent, so this is f prime of x. So this is the derivative of x, which is 1, minus, and the derivative of tangent inverse, it's 1 over 1 plus x squared, right? 1 over 1 plus x squared, and then the derivative of x, which is just 1, okay? So I find the derivative. First thing I do is I find the derivative. Now I set this thing equal to 0 and solve. So 1 minus 1 over 1 plus x squared is equal to 0. I'm going to clear my fraction, so I'm going to multiply everything by 1 plus x squared. So I need to clear my fraction. I'm going to multiply by 1 plus x squared. And I end up with 1 plus x squared minus 1 is equal to 0. So I end up with x squared is equal to 0. So where does this happen? It happens at 0. So that is my critical point. That is a place in which my derivative is equal to 0. And that is my critical point. Okay? So which one of these would you all like to do? A or B? How many of you like trig? You all want to do B? Okay, cool, do B. I would have chose B, but whatever. Go ahead and do B, please. All right, so let's take a look at B. We're going to do the product rule. When we do the product rule, we get cosine x, cosine x. I'm going to take the derivative of sine first. So derivative of sine is cosine multiplied by the cosine that's already there. The derivative of cosine is negative sine. So it's cosine x plus negative sine x, sine x. So I get cosine squared x minus sine squared x. sorry. I'm going to replace one or the other with using the Pythagorean identity. The Pythagorean identity is cosine squared plus sine squared is equal to 1. I chose to use the replacement for sine only because that way I don't have to do a minus, and I just felt like it. And so I'm do a replacement for sine squared using the Pythagorean identity. The Pythagorean identity again is this. What I used to do that replacement is cosine squared theta plus sine squared theta is equal to 1. I just solved for sine squared. And so I end up with 2 cosine squared x minus 1. I set that equal to 0, which means I move 1 to the other side and divide by 2. And I take the square root of it, so I get cosine x is equal to plus and minus the square root of 2 over 2. These are the 45, so it's pi over 4. These are multiples of pi over 4. And so I know this is going to happen in the interval, so it is going to be pi over 4. It's going to be 3 pi over 4. It's going to be 5 pi over 4, etc., going in that direction. So x is equal to. And then going in the negative, it is negative pi over 4, negative 3 pi over 4, etc. So then I just have to figure out which one of these are actually in the interval from negative 0.5 to 2. Well, I get my calculator out, and what is 3 pi divided by 4 with your calculator? Is that number larger or smaller than negative 0.5? I don't know. You all have a calculator. I'm guessing it's going to be larger because 3 times 3-ish is 9. So I'm guessing this one isn't going to work. So I don't choose that one. Is pi over 4 in that interval? Negative pi over 4 in that interval of 0.5? Negative 0.5? Nope. So I don't have that one either. Is pi over 4 in that interval? From negative 0.5 to 2. Is it? Yeah? What about 3 pi over 4? Is that in that interval? I don't know. You get your calculator out. You do 3 times pi, divide by 4. Is that larger or smaller than 2? Larger. So my only answer is pi over 4. So that is my critical point, which is pi over 4. How is that? So it's nothing new. We're not doing anything new. Not at all. So the location of the absolute extrema, so I'll let you read through that. All right, so the location of the absolute extrema says that it must happen in the interior, possibly at the ends, if we have a closed interval, if it's a continuous function. And those points are, if it's a continuous function and differentiable, then it must happen where we have the derivatives. So to figure out where they are is, first of all, you just take the derivative, set the derivative equal to 0, and figure out where those answers are for x. Once you figure out what those answers are for x, you just put that back into your original equation and figure out which is the highest or lowest numbers. So which one do you want to do? Oh, there's a bunch of them. Look at that. I'm all about you all. Which one do you all want to do? A? Want to do A? Okay. So let's go ahead and do A. So the first thing I'm going to do is do the derivative. So f prime of x is 4/3 x minus 1 raised to the the positive 1/3. Positive 1/3. Now I'm going to set this equal to 0. And so I have 4/3. Oh, thank you. So I have x plus 1, 4/3 x plus 1 raised to the 1/3 is equal to 0. I'm going to go ahead and get rid of that fraction in front, so I'm going to multiply both sides by the reciprocal, 3 over 4. And so I get 4, look, I just got rid of it, and I'm just bringing that baby back. So I have x plus 1 raised to the 1/3 is equal to 0. So I take and cube both sides, so I just get x plus 1 is equal to 0. And so I get x equals 1, or negative 1. So is that negative 1 in that interval? Absolutely. So now I have to determine if that's a maxima or a minima. So what I'm going to do is I'm going to just put in numbers on either side of it. I need to know whether or not I'm increasing or decreasing. And in particular, because it's a cube root, I can do that. So I'm going to put in, say, f of -2. And then I'm also going to put in f of positive or 0. I'm going to put an f of 0. I need to just choose something on either side because I need to know whether or not, and then I also have to put the original one back in, f of -1, and do a comparison between these. So if my -2 and 0 produce numbers larger than -1, then that's a minima. If my -2 and 0 produce numbers that are smaller, then that's a maxima. So I can do the 0 all day long. It's 1. Look at that. I put in -1. When I put in -1, I get 0. I can do that one too. When I put in -2, I'm going to get, I don't know what the hell I'm going to get. What am I going to get if I get -2? Is it going to be +1 again?
Yeah.
Okay, cool. So this is where my critical point is. Now, is that number larger or smaller than the values beside it? Smaller, so that tells me my critical value is a minima. And it is the absolute minima in that area. I do need to check my -8 and 8. I do need to check the endpoints. So I do have to go back to my original one and put in -8 and 8. So I have to do f of -8, and I have to do f of 8. Now, because of the fact that I'm taking the cube root and then I'm taking it to the 4th power, cube root of -8 or 8 is going to be -2 and 2. And then I take it to the 4th power. So these are both going to be the same value because it's raised to the 4th power. I'll go back to the function in a minute. And so 2 to the 4th is what? 16? Is that right? 16? So these are 16. So these are where my absolute maximas are. So my absolute maxes are at the endpoints. And we call these endpoint extrema. Now, the reason I knew that I was going to take the cube root and I'm going to take it to the 4th power, and that's because what I had was I had x plus 1 raised to the 4/3. So the 3 is the index, x plus 1, and the 4 can be wrote on the inside. Or equivalently, if my makes my life easier, I can write it to the 4th power on the outside like that. In this case, it made my life easier if I put it on the 4th power on the outside. So that's how come I knew it was going to be -2 to the 4th power or +2 to the 4th power. How was that? Is that okay? All right. Last part of this section is being able to apply this, because if we don't apply it, why the hell do we do this? I mean, why are we doing it? The whole section, all of chapter 4 is all about applying this stuff. So if you have a rectangle with area of 64 meters squared and the perimeter is given by this equation where x is the length of the side, find the absolute minimum value of the perimeter function and what are the dimensions of the rectangle. So what am I going to do to find the absolute minimum value? What am I going to do? Are you ready for this? A derivative. And then what am I going to do with that derivative? Set it equal to 0. So I'm going to do the derivative of this. I know I'm running out of time. So p of x prime is going to be equal to 2 plus, it's going to be 128. And because this can be wrote as 2x plus 128, x raised to the -1. So it's going to be x raised to the -2 multiplied by -1. So I've got 2 minus 128 over x squared is equal to 0. Now what do I do? I'm running out of time. Look, I can do this in 1 second. What do I do now? Multiply everything by x squared. Cool. I'm glad you said that. 2x squared minus 128 is equal to 0. Divide by 2. X squared minus 64 is equal to 0. X must be plus and minus 8. Does it make sense to be plus and minus 8? The answer is no. So x is equal to 8. Thank you. Have a great day.